Okay, good. I hope this picks up sound. Yep. Looks okay, great. I was actually going to introduce myself as Sam Fuller, but I guess I won't be able to do that anymore now. So if you're only here to see Sam Fuller, I'm sorry. He won't. I'll disappoint you, but I'll try to cover as best as I can. Now, I wanted to do this a little bit differently. This originally, I think, was meant as a panel, but from the last meeting we had in Santa Clara, it was a really fun panel the way it worked out because the audience was very interactive. So that's what I hope will happen again here. And actually, I won't give you a choice. You are the panel. You all are the panel. So hopefully you can get very involved. I will ask questions as we go, and you have to raise your arm for one of the optional answers. If you don't raise your arm, I will call on you and make you answer a question. So let's see how this goes. Now, I think Mark didn't earlier mention. Yeah. I work for Avera Semi, which used to be IBM, then ASIC, then became Global Foundries. We're right now spun out as Avera Semi, but we expect to become part of Marvell within a couple of months. So we do high-value ASIC, very expensive components, and we hope to have the most expensive chiplet on these complex systems. So what I want to talk about a little bit is how do we actually build these things? How do we actually stick these very complex modules together? So that's what we're talking about. You know, we have a bunch of different components, and I just wanted to reuse this chart. I didn't really have much meaning to it, but kind of we all put them together. They are non-reworkable once they're joined. So yield is a really important question. Who owns them at what point in time until they're joined is a really important question. How do we deal with all of that? Because there will be fails in the system, and then whose responsibility are those? Now, let's kind of step through the different pieces that become relevant for packaging. First, we earlier heard from Mark that there is a bunch of wire proposal out there that can be implemented at different pitch, right? There's different options of that depending on how much bandwidth you need. You can scale your pitch down a little bit to get more bandwidth, more wires per chip edge. So now, as you do that, and David referred to that already, is you build package complexity as you scale with bandwidth. So for an AIB type of interface, or when you scale that interface, the bunch of wires very small, you'll drive a very complex package. So option one is kind of you leave it at the 130 micron base pitch that Mark already had. That goes in a standard multi-chip package, just in a standard substrate, fairly low cost, or can be done fairly low cost. But if you scale it down and build it at a 55 micron pitch or a 35 micron pitch, now you're looking at a very expensive package solution. Right. So what you pick for your pitch really drives a level of complexity, and with that also cost. So now let's look at our package again and just say there's different components on them, and they all have kind of depends on who provides them and what functionality they have to provide and how much bandwidth. They have different pitch, right? Prepackaged components, probably the most suitable type of form factor for such type of integration because they can be tested and usually come at a 0.4 millimeter pitch or so, versus the ASIC in the middle is probably at a native pitch of 130, but other components, maybe these data converters, could be at 55 micron pitch, right? So now on this example, you have one component at 55 micron pitch that will drive the complexity and cost for the entire solution, because you can't have just one component at that pitch. They all have to be at that pitch. Or I guess EMIB has some advantages there. It's a little bit more modular, but for most package technologies, you'll pay for that complexity for all of it. So we come to our first question. Will a standard chiplet interface prevail? Option one is no, never. There'll always be a number of different interfaces that will coexist.
One who says yes, it will be both.
Number two, yes, in some or a few custom solutions. Number three, yes, in several products. Or yes, this is the future and one interface will be pervasive. So, who's for option number one? Number two?
There's an option where you'll have one interface dominant in each segment kind of thing, right? Like, well, you mean coexist on the same product or coexist in the market?
In the market.
Oh, okay, then I
Okay, let's start over. Number 1. Number 2.
No, I'm number 3. I was
Number 3. You're fast.
3.
And number 4. Interesting. Okay. So now there's a few people who didn't raise their hands. I think, Kevin, you didn't. Okay, you get the next question. Okay, good. One other thought I wanted to bring up, and this is kind of the engineering I do, kind of drawing gray chips on green substrates, and with the letters I indicate how much bandwidth or how many wires I have going out on which sides, right? And that's something we often ignore when we do this PowerPoint engineering. We just put gray boxes without letters in it. So I've graduated to the next level here now. Because now, one thing that is important also is, this connectivity between them. So how many wires, and if I have an F, I need 2 out the side, 1 out the bottom. But now, in another example, I may want 2 Fs on my chip, and the other ones. Now none of these connect anymore. I can't make them connect anymore. Right? So now the question here, Kevin, this is for you. Will standard chiplets be universal enough? No, there's too many variables. Yes, but there will need to be multiple versions of most chiplets. Or yes, a single version of each chiplet will be sufficient.
Can I get an option B?
Yes?
This is what I worry about, right? That if we don't coalesce around standard interfaces and protocols, there will have to be multiple versions of chiplets for each segment. So when I think of the segments, I think system integration into a package, the topic that was raised by David, I.O. disaggregation, logic disaggregation. In each of those segments, there's most likely a standardized interface, or we coalesce around an interface. And if we don't, then there need to be multiple versions of each chiplets.
Mm-hmm. Yeah, and I think it goes also then these chiplets, it goes a little bit also to the previous pitch question. If your chiplet is at 130 micron pitch and big C4 bumps, but it now goes onto the one with micro bumps, does that really work? So.
When you say each chiplet, do you mean, by definition, each chiplet is, what do you mean for one functionality? Like, let's say 8 cores, there'll only be one version of an 8-core CPU. Is that what you
No, really more kind of, take that example. You have a chiplet that you want to reuse once in a system that uses micro bump pitch, and once in a system that has regular C4s. Do you need now 2 versions?
Do you have more challenging substrate technology? Does it move the technology?
You guys will be paid more.
Right. This is that drives the complexity for all of it then. Yeah.
Is it possible that the front end is the same, but back end is
Right. And then therefore 2-part numbers, different derivative, you start having this derivative branch for all of them, yeah.
Which potentially fractures the ecosystem.
Yeah.
Well, I think like C, right? You have one version, but all the packaging guys will make the different and harmonize them in the package.
Yeah, but you run out of solution space there too. Let's look. Some of these parts, when you add so many components, they become too big to put on a 2.5D package. There's a certain limit to that, where it won't work anymore.
So in regular packaging, it's normal for smaller chips to have QFM and CSP and multiple variants. Can that conceivably be the answer?
It could, yeah. Yeah, it's part of the answer, I think, yeah. Not the full answer, because when you need, again, when this small pitch, I think, usually drives the problems. If you can put it in a QFP or something like that with very few IOs, those problems are easy to solve, I think. It's the high bandwidth problem.
So let's say a complicated chiplet is available in 130 or 55. You could choose from both.
Yeah, it's the chiplet, you always want to use the simplest one, so the biggest pitch. But if one other component is 55, then you need to move them all to 55.
Yeah, that's the part I'm not getting.
If you can accommodate the smaller micro bump pitch, you should be able to, in the same package, I would think.
No.
Some drastically different.
EMIB has that capability. Yeah. But I think it's the only one.
Where in one die you have a combination of 130.
Or even mixing. I am not familiar of a 2.5D or wafer level fan-out technology that can operate on one end of it, on one side of it at a very fine pitch, and on the other side at a very coarse pitch.
Or you can fan out each one of them and then put the fanned out components on a substrate.
Right, right. But again, we get into this complexity evolution.
He has this nice chart that shows that it's like less expensive and whatever.
So it all depends on how complicated the technology you're using, right? If you're driving many layers of fan-out technology with really large packages, you are going to see a significant increase in cost.
You're basically arguing for each die to have its own separate fan-out die set glued to it, and then they all get onto a different.
I'm not arguing for it. I'm just highlighting this is as a that's just having chiplets doesn't mean we can always effectively put them together in a package. There's too many other variables. It's
Essentially, you need some kind of an adapter to.
you may that may be one of the solutions. Yeah. Okay, somebody already mentioned, or I think Mark just mentioned substrate cost. This is another interesting part of the equation. Substrate is right now we're coming to a point where substrate costs are growing incredibly. Mostly right now still in other application spaces like networking, wired networking, where it's more driven by high-speed SerDes in the 85, 90, 100 millimeter space. And what we're learning as we go through that is that the substrate cost becomes astronomically expensive. We're talking about $1,000 or $2,000 substrates for regular substrates. Now we're saving money on the silicon side when we partition chips, right? They become better yielding smaller chips, but we spend more on the package side. So it's very possible that there is an inflection point, right? And that's the next question. And I'm going to pose it to all of you again. Will package cost be a concern? Is it on the radar? No, this is not significant. Maybe, but the savings are probably much higher. Or yes, there will be a point of negative return, an inflection point. Option 1. Option 2. Option 3.
You already told us the answer.
I would add the weighting on this. I mean, there's certain solutions that will be more expensive that are only viable in a single package solution. So for example, if you're a chip supplier and you want to add some other type of technology and you don't have that technology, you can't do it.
Yeah.
All you can do is partner.
Yeah.
So even though it may be more expensive, the integrated value may be higher or may offset the increased cost.
Yeah, agree. Good point. Yeah.
I agree with that. It could actually, you'll pay more for the package, but that'll be the only alternative for that solution.
So Wolfgang, you're bringing but organic package?
Yeah. It's a step function if we go up then to a 2.5D type.
So what is the reason for substrate cost to skyrocket? Is it high density?
The panel utilization becomes very poor, and the yield concerns are huge. And the substrate world really has not learned their way through this yet. I think they're in the middle of it. But there's the quote responses we're getting right now are incredible. Okay, another topic, bill of materials and where do the components,
Would you mind going back to 2 slides?
Yeah. This one?
That one. What's that number in the x-axis? Is it like 5, 10, 20?
Yeah, I think it really depends on the system. I mean, if I look at their Nirvana out there, just the components alone on that thing must cost a couple $1,000s, is my expectation. So But then simple systems could start probably at $50. So.
When more chips, when you see that substrate curve, the green line at 5, 10.
Oh, where does it become so steep? Okay, yeah. I'd say up to about 65, 70 millimeter is still a relative predictable curve. But beyond that becomes...
In terms of number of components?
No. Yeah. Okay. Good. So, bill of materials, where do these components come from? Are they going to be there? There's just many things that can happen, and you can write this list endlessly long. One component may not tape out, or they come in your truck and you got a flat tire, and then all of a sudden you don't have that chip that you need to build that MCM. One component could cause significantly yield fallout. It could be because the C4 bumps got a little bit dirty, or they're not joining, or they're different composition than all the other ones. All components may meet spec by themselves, but the MCM functional yield is still low. Could be some interaction between the components, right? One could draw more current and take away from the power supply of the next one. Components could change over time. They may shift to a different fab, may have a different bump type in the next generation that's all of a sudden taller, and now your component height is taller, doesn't fit under the lid anymore. One component could fail after 6 months in the field, or could go end of life. There's just an endless list of things that just change on products. It just happens. So the question... you mean if it changes over time, or just as a general concern?
Yeah, like different breakpoint and
Right. If you, for example, stick a DRAM on there that can only go to 85C, yeah. Okay, so this whole thing about component availability or the flat tires question then to you again. You could say this is no different than what we have today already at system level. You could say it's going to be a growing pain, but it'll be okay. Or this will be a substantial logistical challenge. Option 1? Option 2? Option 3? Okay, so pretty mixed, pretty balanced, yeah, interesting. Yeah.
He does this for a living, so. And he chose option 1.
So do you want to explain it? The thinking?
So the way we think about it is we are essentially making a PCB, but it's just made of silicon. We're buying components which are otherwise sold to be used on PCBs. They are wafer level chip scale packages. They come with same warranties, like 500 DPM. So we are just exercising the same supply chain. We have same problems. So like this particular lot had some issue, but if I were to be building it on PCB, would be the same thing. And testability, system level test problems are the same. It becomes complicated when you start pushing pitches really, really small. But I believe that is just a matter of time, right? Where we are dealing with this problem, pitches are in 130 micron, right? When it goes to 55, 3-4 years down the line, I think it would be very analogous to the supply chain issues of today.
Are you considering rework when you're thinking about that?
You can't really rework a PCB in volume.
Okay.
Once you build a big lot, right? But truth is that today there are labs available that can actually rework MCMs for debug, right? And you can also conceive of circuitry that would do built-in self-test inside the silicon interposer that you would need the rework for. Those kind of innovations will come, I believe.
Okay, thank you. Good. Going back to the cost question, one interesting point I think is value add and margin stacking.
This is the previous thing.
Yeah.
Today we have a pretty well-established assembly houses which can deal with the system levels. This is brand new. So there will be an inflection point until, there are many people who will jump into manufacturing these things until they find it viable. And the other side is, it'll not become viable until multiple people jump into it. So there's going to be,
Yeah, yeah,
I mean, it's going to go through a pinch and then expand.
yeah, yeah,
That's what I'm thinking.
yeah. Okay, back to the money. Value add and margin stacking. For an end customer, it's always easiest to just buy a completed module, fully tested, everything works, right? But for a supplier, to own that responsibility and carry the inventory and deal with all the fails that may happen, it's a substantial added burden and risk. So there's going to be added margin on top of the margin that's already by the original chiplet manufacturer. So how is this going to work? Is this expected, and 50% is a reasonable cost adder for on top of the component cost? Is it going to be 20%? Is that tolerable? Or there's no more room than like a 5%, a single-digit number? So option number one.
Software value add.
It's going to vary by market segment.
Mm-hmm.
I think you're going to have some where the margin stacking is going to be very high and won't be noticed, and other segments that are going to be very cost sensitive.
Mm-hmm. Mm-hmm. Yeah, yeah, good point. Yeah.
It'll be kind of the early adopters will be on the top, and the mainstream is going to be at the bottom.
Mm-hmm. Yeah, yeah. So more by early adoption and complexity than by general market, yeah. Yeah. Okay, good. Then no introduction for the next one, but I'm just curious. What's the bigger challenge? Is it technical for chiplet adoption? Is it business, or are they kind of equal? Who thinks technical has the biggest challenges? And who thinks business has the biggest challenges? And who thinks they're the same? Very mixed, yeah. Okay. Good. Now, in terms of who is going to own the integration, right? You could say maybe the company who provides the most complex part, the highest value component, may be a good candidate to own the integration, to build that whole module and test it and ship it to the end customer. You could say the OSAT is best positioned to inventory all these parts and build them the way they use passives today, which are obviously much cheaper. A fab partner could own all of this. There's maybe room for a new integrator who takes care of all of that, or the end customer. Any thoughts?
I think it's going to be a new integrator. This expertise doesn't exist.
Mm-hmm. Yeah, yeah. And
I find it highly unlikely to be a fab.
yeah, yeah. And I think also from our perspective as an AC company, it's unless we can charge a very high margin, it's not a business we want to necessarily be in, to inventory components and own yield on other people's components. Any other thoughts? No? Okay, good. Then we're coming to the last one, and I want to introduce that. I used these graphs a couple weeks ago at the last ODSA meeting, and I got a lot of pushback, and I was a bit surprised, honestly, about the pushback. So the upper graph is just cumulative yield over number of components under certain assumptions. And the assumptions I made here was 95% functional yield and 99.5% assembly yield per component. Right? So that's kind of, I think, where we are today if we build single chip modules. It's kind of normal. And you can see as you increase the number of components, you really can't yield them anymore. Right? Even at 5 components and below 80% yield, it's just not going to work.
I think the pushback you got was the the multiplying the yields as to get the yield of the overall product.
I think there were kind of the counter arguments was that there's going to be other solutions.
Right? If the mode is never exercised, let's say your yield is not uniform across all modes. If a particular mode is never exercised in the integrated package, then 95% yield. As far as that mode that you're interested in, you're at 100% yield. So it's not clear that the yield
Is necessarily, okay,
effective
yeah.
yield that's reflected at the system level.
Mhm.
If that makes any sense. I don't have a better term, but it's the yield of what matters to you from that component as a part of your overall functionality, and that's the pushback that I was thinking about it after.
Okay. I have not thought enough about that piece of it, yeah.
But that's the deal.
Uh-huh.
Yes, it's 95%, but if the 5% of the functionality is missing doesn't matter to me, then I don't care.
I think the obvious logical extension is, does the 99% case fit our expectations? Right?
Yeah,
Wolfgang's
so-
outlined of an upper as good as it can get.
No,
is
it's
that
more
as
the
good as it can
product
get?
of the deal. I think the pushback is not around whether 99, 95, is that you're going to make the product of all the yields to get the yield of the overall component. It may not be a reasonable assumption.
It's too pessimistic.
Yeah,
Uh-huh.
that's too conservative
Mhm.
in its estimate.
Yeah, but we will never be at 100%,
Yeah. That's
right? So it's going to be somewhere, and maybe that 99% is still a pretty optimistic number. But even if we look at that, I think it's a pretty expensive game.
It's expensive.
Yeah.
That's fair.
Yeah.
Have you ever asked the question, how many components people envision?
I was counting Dave's boxes on his charts. I think there were 7 on there. Yeah, I mean, if we're just looking at these curves and kind of envisioning, I think 5 is a good starting number. I don't really see more than 10. That seems too much. But that's a great number. Oh, great question. Any other numbers?
We do 7.
Conversations we have are between 2 and 3.
Yeah. For a lot for that reason, probably. Yeah. Okay, good. So the final question, MCM final test yield. This will never work. There will be significant yield loss, and this will limit adoption. This is a concern, and we need to do some more work to overcome this challenge, or this is a problem and we know solutions.
I want to know your mood when you came up with all this.
You say that there's always at least one person in the room for each of these questions.
Okay, Bobby, you want to take this one?
Wait, what? I think it's number 3. Once it's economically valuable, there will be a solution.
Yeah. Any other thoughts in the room? I see somebody smiling.
Number 3 or 4?
3 or 4?
Yeah, I would agree, it's somewhere between 3 and 4.
Mm-hmm.
Room for the walk.
We have this in production now.
Yeah.
We're surviving. It's a high value component.
Mm-hmm.
Making it work.
Mm-hmm. Okay. Good. That was my last question to all of you. So thank you very much to the panel. Appreciate it.
Thank you.
And yeah,
Thank you.
and that was fun. Let's do it again.